Okay, good morning. All right, so exams coming up. It'll be on Thursday, September 17, 6:30 p.m. to 7:30 p.m. We're all spread out. Where you go depends on who your recitation TA is. For example, if your recitation TA is Taylor Daniels, please go to Physics 112. If you are in Emma Reed's class, please come here. And if you are in Matthew Weaver's class, please go to Weather Road 200. Okay? So where you go depends on who your recitation TA is. Okay, let me talk briefly about the exam. There will be 12 multiple choice problems. Lessons 1 through 8, so it does not include what we are doing today. Covers everything up to what we did last Friday. To prepare, look over your homework. The exam is mostly based on your homework. There are two pretty good old exams to look at. One is from fall 2014, and the other one is from spring 2015. And you can get these by going to the course webpage, math.purdue.edu/MA162, and click on the old exam archive. The thing about spring 2015, you want to ignore number 11 and number 12. Okay? Last spring, the exam was a bit later, so we had more stuff on the exam. 2014, you look at every single problem. Okay, and then Wednesday in class, I'll give you a brief review of everything we covered. Thursday recitation is another review class, so we'll give you a little bit of time to ask questions and prepare. And if I can find other relevant review questions, I'll send them to you by email. Questions about the exam? No? Good. All right, let's look at a new chapter today, chapter 7, section 1. We're going to look at a technique of integration called integration by parts. So every technique we have in integration is a differentiation technique in reverse. For example, when we do integration by substitution, what actually goes on is this is reversing the chain rule. And integration by parts, this is the product rule in reverse. In other words, we're integrating something that we had gotten by applying the product rule, and now we want to undo the product rule to get back the function we started with. Okay, so how this works, let's look at how product rule works first, and then we'll see what we can learn from what we already know. I hope you remember the product rule. If I want to take the derivative of a product of two functions, say u times v, how does it go? I hear a lot of mumbles. How does it go? So we take u, this is the first, right, times the derivative of the second plus the second times the derivative of the first. And you can reverse the order of these two because it's a summation. The order is irrelevant. So here I had first times derivative of the second plus second times derivative of the first. You could have done it the other way. You could have this come first and then this second, right? Okay, so that's the product rule. Now I'm going to write them in the differential form, getting rid of the dx all over the place. And then, let me rewrite this one more time. Let me isolate u times dv by itself. So I want this thing on its own side. And I'm going to subtract this over to the side with the duv. And then I'm going to integrate that. Okay, u and v are just some arbitrary differentiable function. Finally, when I integrate d of something, the integral and that d cancel. So I end up getting just the uv. That I can't deal with just yet. So I'll leave that alone. So you can see we end up getting a formula that looks like this. The integral of u times dv is equal to uv minus the integral of v du. What this is saying is that if you're given an integration problem, if we could rearrange the integral in the form of u times dv, then the right-hand side provides what we need to do to perform the integration. Let's look at one example, or the first example, to see how this works. Here we want to integrate the product of x times natural log of x. In other words, there is some function out there whose derivative is x times ln of x. And we would like to know what that function is. So the key is to turn this into the form of u times dv, because then we can use the formula on the last slide, uv minus the integral of v du. So let me show you how this works. I'm going to make two substitutions here. I want to call natural log of x u, and then whatever I didn't choose to be u, I will call that dv. And then what's next here, note in the formula that we saw in the last page, remember, now I've identified u and dv. But to complete the integration, I need to know v. I also need to know du. If I have u, then du is simply the derivative of u. So du is, what's the derivative of natural log of x? Good, very good. Now we need a dx. It's in a differential form. If I have dv, then to get v, I do an integration. So I integrate x, and I get x squared over 2. Okay, so now I got everything I need to complete the formula on the right-hand side. So we can finish the integration. What I wanted to do in the first place is equal to u times v, u times v, minus the integral of v times du. And here's du. All right, uv minus the integral of v du. Then we simplify things a little bit. Let me rewrite this. We often see x squared. X comes before natural log of x, so just rewrite a little bit. And over here, I have 1/2 x squared over x. That's just an x to the first power. So what I got left to do here is just a very simple integral at the very, very end. And I get and remember some arbitrary constant c. So this must be the function that gave us this as the derivative in the first place. And by applying integration by parts, we undid the product rule which gave us this in the first place. By the way, let's make sure that our answer makes sense. Let's do a check. When I take the derivative of this, I better get x times ln of x. Right? If I don't, then this is wrong. Now you see the first group here requires product rule, right? We have product of two functions of x. So here's the first times the derivative of the second plus derivative of the first times the second. That's just a simple integration derivative, power rule, 1/2 x. See the constant goes away. One half x cancel out, and we get x ln of x, which is what we started with. So therefore, this is the right answer. We got the right answer here by performing the process of integration by parts. Questions on this? Yeah. That's a good question. I'll cover that in a little bit. Other questions besides which one to choose to be u? Okay, now let's look at the u question here. First of all, let's see what happens if I had made the other choice. Basically, you have two choices. You got two things to choose to be u. I chose natural log of x to be u, and things worked out pretty well. Let's revisit that same problem. And this time, what if I let u be x, and then dv? dv is always what you didn't choose to be u. dv is the leftover stuff, right? I chose that, and these guys are the leftover. Then du is simple. When I get to this part here, now I get into a little bit of trouble. The integral of natural log of x. Derivative of natural log of x is simple. but integral is not. This is not a trivial thing here. So what we end up having as a problem here is something that's not much easier than what we started with. So this is one symptom of what happens when you choose the wrong u. Difficult or impossible. Okay, so when you start out, if you're not used to the process yet, you're going to choose the wrong u eventually at some point. When you find out that this integration is very difficult to perform, perhaps more difficult than the integration you wanted to do in the first place, that's a sign that you chose the wrong u. Go back and switch around. Here's the rule of thumb in how to choose u. So we choose u in this order. If you see any part of the integral that's logarithmic, any kind of log, natural log, for example, that is your number one choice to be u. Always choose log before anything else to be u. Next best choice is inverse trig functions. Inverse sine, inverse cosine, inverse tangent, for example. Whoa, what did I do? That's still not right. There we go. Inverse trig, get it? Inverse. Next one, algebraic. These are things like x squared, square root of x, x cubed, that kind of thing. Next one, trig. And finally, exponential. Exponential. Yeah. So they spell out this silly little word that tells you which the hierarchy in which you choose your u. So log first, inverse trig next, algebraic, trig, exponential. In other words, e to the anything, that's your very, very, very last choice. Anything else must come before e. So you see what happened when we look at x times ln of x. In the second choice I made, I chose an algebraic before a logarithmic, right? So I run into a problem. There are functions that you can actually change the order and still get away with, but in general, this is the easiest way to approach all of these problems. Okay, let's do a few more examples. And we'll focus on what we let u be. So here we have x times cosine of x. So x here, this is the algebraic part. And obviously cosine is the trig part. based on the order we just established, we want to choose the algebraic before trig, right? So we want to choose u to be x. And once you made a choice of u, whatever you didn't choose, all of that gets lumped into dv. I didn't choose cosine, I didn't choose dx, so all of them get lumped into dv. Then I take one derivative of u. I do one integration of dv. What's the integral of cosine? Sine. Good. Right? Okay, then we use our formula. uv minus integral of v du. And we get x sine of x minus, so that's uv, the integration of v du. And you often find out that this last integral that you have to do is closely related to the integration you did from dv to v. It's often the same type. So dv to v, we integrated a cosine. Here, the last integral to do is integrating a sine, which is closely related to cosine. So here we go. We get x times sine of x plus cosine of x plus some constant c. Okay? Questions? Let's also find out what happens if I had reversed the choices here. Let's see if this one is as bad as the natural log of x. Revisit that again. Okay, so here I went against the rule of thumb. It's just a rule. It's not something that you have to follow all the time. It helps. But occasionally you can get away with changing the order. So if I do that, then derivative of cosine is minus sine. Don't forget your dx and your du. And then integral of x is 1/2 x squared. Okay, then we do that. U times v minus the integration of v times negative sine of x. Simplify a little bit. Okay, the minus signs cancel, gives me a plus, and I pull the 1/2 out. Now check out what we have left to do. Compare that to what we started with. It got worse, right? The power of x went up by 1. If I do another round of integration by parts, I'm going to end up with something probably x cubed sine of x. That's not taking me anywhere constructive. It's a waste of time. I end up getting something more and more complicated. So again, this is another typical sign that the choice of u is wrong. Sometimes you could integrate your dv, but then when you get to this part here, you get a harder problem than the one you started with. That's a very, very common sign of choosing if you chose the wrong u. Let's look at that problem one more time, but this time I'm going to change the exponent of x a little bit. When you look at this compared to the last one, it's basically the same type of function, except x has a higher power now. But it is still an algebraic part versus a trig part. When you go through the order, what you choose to be u is still the same, right? We always choose algebraic before trig. Then we differentiate u. And we integrate dv finally uv minus integral of v du, and we get uv minus the integration of v times du. Okay, now we got here, we got one last integral to do. What do you think we should do to it? Yeah, it's exactly the same, very similar to the last problem we did. Last time we had x times cosine of x. Here we get 2x times sine of x. This is another integration by parts. Right? Integrate by parts. So we go through another round of this stuff. So once again, I'm looking at here. I'm going to choose u to be, what should I let u be? 2x, good. And dv is whatever I didn't choose. Take one derivative, integrate once. You got to be very careful that these uv, once you made another set of uv here, be careful you're looking at the right set of uv. So only this part is using that set of u and v. Okay, now we have minus. Now we do another one of these. uv minus the integral of v times du. So these go into here. Simplify a little bit. minus, 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 so a net is a negative. And let me take that 2 out of here. By the way, I could have taken a 2 out earlier, and then that's going to modify my u here. It's the same in the end. You could take a 2 out earlier, or in the end end up doing the same thing. It doesn't change anything significantly. The process doesn't change significantly. Of course, the answer has to be the same. Let's see. That would be, let's see, negative 2 sine of x plus some constant of integration. Which one? Okay, let's go back here. Here, these two minuses turn into a plus, right? Then I have a minus the whole thing, so this makes this a negative 2. And when I integrate cosine, what do I get? I get positive sine, so I retain the negative sign I had earlier. Negative 2 times the integral of cosine, which is positive sine. Okay, are we okay with the signs here? Question? Which dv are we looking at? Good question. Why didn't I get a plus c here? It turns out that if I had a plus c, then I ended up with some constant at the end again. So in the end, what you end up doing, you can try this on your own, actually. It's a pretty interesting thing to find out. In the end, you lump that into the constant which you get here. So we just make the process simple to make that step a little bit more streamlined. So you could add a plus c here, but then you lump two constants at the end into another constant. Good question. There was another hand. Nope? Okay. Say that again, please. Right. Yeah. So let's compare that to the first problem we did. When I had x to the first power times cosine, I integrate once, right? I do one round of that. When I bump the power to 2, I had to do 2 rounds. So we can generalize this and say when I have x to the n times a trig function, I have to do the integration by parts n times. And that's the same kind of thing you would see if this were an exponential function. X times e to the x squared times e to the x behave very much the same way. The power here often tells you how many rounds of integration by parts you have to do. Does that answer the question? Okay. Other questions about this? So, by the way, how would you deal with definite integration then? You do exactly the same thing. You drop your plus c, and then you integrate 0 and 1, right? So if you could integrate indefinitely, then definite integration is the same thing. Drop your plus c, and then evaluate. Let's have one with an inverse trig. Sometimes you only have one thing to choose from. Like in this case, we have cosine, inverse cosine, and just dx. In that case, imagine you are doing inverse cosine of x times 1. And 1 is like x squared. It's an algebraic part. According to the rule of thumb, we want to choose inverse trig before algebraic. So I chose my u, and whatever I didn't choose to be u, everything else gets lumped into dv. All right, so who remembers the derivative of inverse cosine? 1 over something. Yep. What's that something? It's a negative. Good. What's this something down here? So close. How about that? All right, don't worry you didn't know that. I mean, well, okay. Don't worry if you had to look up to find that. It's not something we encounter very often. Okay? All right, so the other part here, what's the integral of dx? Just an x, right? Okay, then we go through our uv minus v du. And let's see, what do we get? We get uv minus the integral of v times du. Let me do it this way. Okay, what do we do here then? Right, substitution, a u substitution, excellent. We let u be 1 minus x squared. Du is negative 2x dx. Once again, be careful. I'm reusing the symbol u, but that's okay, because once I got here, I don't need the previous u anymore. Now I just deal with this part of the problem. All right, so I have u under square root downstairs, which turns into u to the negative 1/2. And then x times dx turns into negative 1/2 du. And now we got a pretty easy integral to finish. What do we get? We get minus 1 over 4 no. Yeah, I think that's it. Is that right? And now u refers to my second u, right? Be careful now. So there we go. So the first set of u, that only got me to after the integration by parts. The last integral I had to do had nothing to do with the first set of u and dv and all that. The second set of u took care of the integration by substitution part of the problem. Questions? Yeah. Okay. So are we good up to here? You're okay up to here? We want to go from here to here. Is that what you want to see? Okay, got it. So I'm integrating that. That minus 1/2 is irrelevant. I pulled it out. Then I'm just integrating using the regular power rule. I add 1 to the existing power, and I divide by the new power and some constant, right? Power rule, add 1 to it, divide by the new power. And the 1/2 and the 1/2 cancel. I retain my negative. So that's where this thing came from. Is that okay? Okay. Other questions? All right, let's do one more, and then we'll end it there. So here I changed the function to e to the x times cosine of x. We go through our progression again. Remember, exponential is always your last choice. When you see exponential, avoid it and choose whatever else comes after it or before it to be u. Then we go through the usual steps. All right, then uv is e to the x, cosine of x, minus the integral of e to the x times minus sine of x. And the 2 minuses turn into a plus. Okay, what's that? Not forever. At this point, you look at this and you go, that's where I started, right? Well, almost. But trust me, we're going to do one more round and you'll see how we can make this work. So let's see. E to the x, cosine of x, Now this stuff here, we do that again, but with this set of choices of u and v. So we get e to the x sine of x minus the integral of v du. And we're back to where we started. But that's okay. This is the problem we're trying to solve. And all of these things tell me that what we're trying to solve is equal to all of this stuff. Right? Notice this shows up on both sides. So what if I add this over to the other side? Then I get twice of what I wanted. Right? I get twice of what I wanted. So what I really want then, what I really, really want is this. And I know I'm going to need a constant, so I'm just going to put it down here, plus c. So there we go. There are times that it looks like you're going nowhere, but actually end up where you started with. In that kind of situation, you need to remember what you're solving, and then lump those things together, divide out the constants, and then solve your problem. All right, that's it for today. See you Wednesday.